Here we have your exercise on directional derivative. Here you are to find the directional derivative of the following surfaces at the given points in the direction of the given vectors. So question 1, f of xy is 6 minus x cubed plus 9y squared plus 15xy. That's the curved surface at the point 1, 2 in the direction of the vector u is equal to sine 1.5i plus cos 1.5j. Right? And remember, you need to do all of these questions before you watch my solution of the questions. Alright? And later on, I'm going to do a review of the steps that you should take when finding directional derivatives. Alright, question 2, f of xy is equal to x squared plus y cubed at 5, 2. And in the direction of the vector, u is equal to 2/3 I plus square root of 2 over 5j. So remember, you should write all of these down on paper and work them out. Question 3, f of xy is equal to negative 8xy minus 4x cubed plus 16y to the fourth at 1, 2. The vector is the square root of 3 divided by 3i minus square root of 3 divided by 3j. Question 4, f of xy equals x cubed plus y cubed minus 3 at the point 2, 2 in the direction of the vector. Now in this case, the vector is written as a column matrix. Square root of 3, square root of 2, square root of 2. It's the same thing as saying the square root of 2i plus the square root of 2j. Alright? Where, of course, the element in row 1, the top, is in the I direction and the bottom one is in the j direction, right? Number 5, f of xy is equal to 4x to the fourth plus 3y cubed minus 2x squared y squared at the point negative 1, 1, and the vector is 2i plus 3j. And number 6, f of xy is equal to x squared plus y squared at the point 1, 1. The vector is I plus j. Same thing as 1i plus 1j. Alright? Now, just a reminder, when you're finding the unit vector, the way it is written is to say directional derivative. Or did I say unit vector a while ago? No, the directional derivative, I should say. Directional derivative of the vector of the function is Nabla f dot u with the hat over it. That's the unit vector, alright? So it's the dot product between two vectors. There's the gradient vector, upside down triangle, which I call Nabla. Right? That's the gradient vector of the function. That's the dot product between that vector and the unit vector. Right? So remember what to do. Step 1. You find the gradient vector. So this gradient vector is Nabla f. It's equal to the partial derivative of the function with respect to x, I, plus the partial derivative of the function with respect to y, j. Alright? Now, step 2, you find the unit vector. Alright, so remember, if you're given the vector in the form A plus AI plus BJ, and by the way, remember, sometimes the vector is given in this form as well, right? The angled brackets mean it's a vector. The one on the left is in the I direction, the one on the right is in the J direction, right? So it's AI plus BJ. But sometimes it's given like this. Alright, so you're given AI plus BJ. Remember, the magnitude of this is the square root of A squared plus B squared. Alright? So remember, you have A in the I direction, and you have B in the J direction. You're at 90 degrees, so you apply the Pythagoras theorem. Is really the length of the hypotenuse you're looking at here. The square root of A squared plus BJ, right? I mean, the square root of A squared plus B squared. We're talking about BJ. Alright, so the unit vector would be AI plus BJ over the square root of A squared plus B squared, alright? So you really divide the vector by its magnitude. Now, you get the unit vector in that case. It's just like you have a number divided by this itself. You get the unit number, which is 1. The unit vector, right? And you use unit vector because, remember, you're finding the dot product here. Now, if you multiply a number by 1, you get back the same number, right? The 1 might not be this. It might very well be 5 over 5. Well, it's like when you're finding, when you're adding vectors, or when you're adding fractions using common denominators, right? Multiply the top and bottom by the same number. It's like multiplying by 1. So the way the number looks now, it looks different, but the value remains the same. Alright, so in this case, you're dotting between a vector and unit vector. The value of the vector remains the same. You're dotting with unit vector. Alright, so when you do this, you're going to write it out as A over the square root of A squared plus B squared, whatever that is, I, plus B over the square root of A squared plus B squared, J. Alright? That's unit vector. And then, after that, step 3, you find the dot product, the gradient vector dot unit vector, right? So in that case, Nabla f dot unit vector is equal to what you add up here, delta f by delta x delta plus delta f by delta y I and j, delta f by delta xi plus delta f by delta yj, that product between that and this up here, a over the square root of a squared plus b squared, I plus b over the square root of a squared plus b squared, j. And what you get is a scalar. You won't get any I and j there. So remember, is going to be I by I. We're doing I this times this plus this times this, and you get a number, a scalar out of this, right? You're not going to have any I and j in the answer. It's not a vector, it's a scalar. All right, so you have the steps here and the exercise. So answer all 6 questions, and then I'm going to work out the solutions myself.